right, so suppose that we've got two functions, and they each have Taylor series centered at the same point. All right, it doesn't have to be 0, but it's less writing if I just make it 0. All right, if it wasn't 0, then all the powers of z would be powers of z minus z naught. Right? So I'd like to know what is the series for the product of these two functions. Okay? Well, I mean, we can go back to just standard FOIL. If I multiply these two series together, I mean, look what I get. I just get A1, B1. Plus A1, B2, plus A2, B1, plus A2, B2. Right? So I get all possible products consisting of a term from the first sum and a term from the second sum. So for that reason, I would just get that. Two sums take place independently. That's why we needed to have different indices. I needed to have J and K. If I had tried to write both of them with K, it wouldn't make any sense, because it's like it would couple together the two sums. And the two sums are not coupled. They're independent sums. So I need a different index for each of them. Now, obviously, if I want a Taylor series for f of z times g of z, I don't want to have some random combination of all kinds of different powers of z. I'd like to have a coefficient for z squared, a coefficient for z cubed, a coefficient for z to the 7th, and so on and so forth. So the power here is j plus k, z to the j plus k. So what I'm going to do is I'm going to rearrange the terms based on what power of z they're associated with. Now, this rearrangement can only be done in a meaningful way if the two series both converge absolutely. I require absolute convergence to be able to do the rearrangement that I'm about to do. Now, if I push it all the way to the edge, I could have one of the series converge conditionally. As long as one of them converges absolutely, it can be shown that the rearrangement I'm about to do works well. But if they're both conditionally convergent, then it won't. All right? But at any rate, we're not worried about that. We're going to only do this rearrangement inside the disk of convergence. And remember, every Taylor series converges absolutely inside its disk of convergence. It might converge conditionally on the circle of convergence, but it will converge absolutely inside the disk. All right? So I'm going to let n equal j plus k. This manipulation is sometimes tricky for people, so I'll do it slowly. I want to graph J versus K. J and K are both going from 0 to infinity. So I'm adding up all of those points. Right in, if you like, the first quadrant. I'd like to change that over to a sum over n. Obviously, n will have the smallest value, and it will go up without bound. Okay? That's not the tricky part. The tricky part has to do with what happens at constant n. Well, constant n is associated with sums like this. See that? N equals 1. N equals 2. N equals 3. N equals 4. All right, this is n equals 0. So at any particular value of n, k will go from 0 to n. All right? And that's because, for example, if n equals 6, k can't be 7 because n equals k plus j. And j has to go from 0 on up. If k was 7 and n was 6, then j would be negative 1. And j can't be negative. All right? So I'm only summing from 0 to n. J is n minus k. And so this becomes my coefficient for z to the n. Notice that the indices on f and g add up to n. So as an example, c sub 3 is equal to f3 g0 plus f2 g1 plus f1 g2 plus f0 g3. All possible combinations that could give me z to the third. All right? This combination here unsurprisingly is named after Cauchy. It's called the Cauchy Product. All right? Cauchy Product. Now, let's take a couple of minutes to use the Cauchy product to determine a series we don't know. Oops. Let's just do the first 4. All right, I'd like to determine the first four non-zero terms in the Maclaurin expansion for the tangent function. Now, I said we were going to use the Cauchy product, but then I do a function that is a ratio. It's not a product, it's a quotient. So how are we going to use this? Well, here's what we're going to do. This is equal to, let's call it f of z, and that's equal to sine z divided by cosine z. Cosine z is going to be g of z. So sine z is equal to tangent z times cosine z. All right, so that's f of z times g of z. All right, I know the expansion for the sine function. I know the expansion for the cosine function. And I know the Cauchy product. So I'm going to use those things in conjunction with each other to determine the expansion of the tangent function. All right, which are the f's. So let's call these the h's. All right, and I would have h0, which by the way is 0, because sine z's expansion starts with z. All right, h of 0 is equal to h0 is equal to f0 g0. All right, g0 is 1. So that means f0 is 0. Remember, g of z, that was the cosine, 1 minus z squared over 2 plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, and on and on and on. So this is where I'm getting my g's from. My h's are coming from this. All right, so let's go to the next one. H1. Well, H1 is 1. That's going to be F1 G0 plus F0 G1. Well, we already said F0 was 0. So that means this is just F1 G0. So that means F1 is 1. What about H2? Well, H2 is 0. Just like that. G1 is 0. Right? F0 is 0. H2 is 0, which means F2 is also 0. By the way, the tangent function is an odd function. So if you're looking at all these products and you're saying, oh, well, you know, the even ones are all 0, that's because they're mismatched. Sine z is an odd function. Tangent z is an odd function. Cosine z is an even function. All right? So for that reason, we don't really need to look at H4 and H6. All right? So So let's go ahead to H3. H1 is 1. All right, what about H3? Or sorry, F1 is 1. H1 is also 1, but anyway. All right, so this is going to be F3G0, F2G1, F1G2, F0G3. Remember that G was an even function. So that's 0, that's 0. Okay? H3 is negative 1 over 3 factorial. F3 I don't know, but G0 is 1. Then I've got F1 G2. So that's 1 times negative 1/2. All right, so F3 is 1/2 minus 1/6, which is 1/3. All right, let's look at 5. All right, so it's going to be F5 G0. F4 is 0. So I'm just going to do F3 G2, F1 G4. All right? So I would have negative 1 over 5 factorial equals F5 plus F3. That's a third. G2 is negative 1/2. F1 is 1. G4 is 1 over 4 factorial. So that gives us F5. F5 is equal to a 6 minus a 24th minus 1 over 120. So this is equal to a 6 is 4 over 24. 4 minus 1 is 3. 3 over 24 is 1/8. All right? 120 is 3 times 40. All right? So that means that I need 15. All right, so it'll be 15 divided by 120. That's not right. That's not right. I made a mistake. Let's see. 1/24. Let's see. 1/8 minus 1/20. 1/6 minus 1/24. Oh, it's plus 1/20. Sorry. Plus. All right, so that's going to be 16 over 120, which is 2 over 15. All right, and we can continue with that. You can see that this is a systematic way to determine the coefficients, even if it's a bit annoying. All right? Now there is another way to do it. By the way, notice we didn't determine the first 4. We only determined the first 3. Let's see what we could do if we do it a different way. Okay? So this was one way. This is a very organized way to do it. But it does take a lot of writing, a lot of space. Okay? Let's see if we can do it a different way. And I'm just going to go ahead and remind ourselves of what we've already gotten. So as an alternative, we could use a sort of less orthodox approach. So we could say all right. Now, what do we got here? Sine z divided by cosine z. So this is z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus z to the 7th over 7 factorial plus dot 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 divided by just like that. All right? So now if I wanted to, I could view this as that. And now I can view this as a geometric 1 over 1 minus box. And now I could expand this out if I wanted to. Z over 5. So it's a geometric. So that's going to be 1 plus box box squared, and then plus dot, 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 dot. So at this point, I can rip out the coefficients that I'm interested in. Now this looks like a lot of writing because this is the first time that we're doing it. But really not that bad. Look what we've got. I've got an overall factor of z. How can I get 1? Well, it would be 1 times 1. 1. All right, so there's my first term. All right? How can I get a z? Well, I can't. They're all z squared. How can I get a z squared? Well, I could get it from here, or I could get it from here. All right? So there I've got z squared. How can I get a z to the 4th? Well, I could get it z to the 4th over 5 factorial times 1. Or I could get it minus z to the 4th over 4 factorial times 1. Or I could get it as z squared over 2 factorial squared times 1. So that's plus 1/4. All right? And finally, I could get it by multiplying negative 3 factorial times z squared over 2 factorial. So that's going to be minus 112. Like that. And we can work through this. Let's see what we get. 1 over 5 factorial minus 5 over 5 factorial. And then a fourth minus a 12th is a sixth. All right? A sixth minus 4 over 5 factorial. A sixth minus 1 over 30. So that's 4 over 30, which is 2 over 15, which was what we got before. All right? To get the z to the sixth term, I would need this times 1. That's going to give me z to the sixth. I could do z to the fourth times z squared. That would give me z to the sixth. I could do z squared times z to the fourth from here and z to the fourth from here. That would give me z to the sixth. Or I could do 1 times z to the sixth here, the cross term here, or the cubic out there. All right? So we could go ahead and do that. I don't know that it's worth the time at present.